Okay, so next set of notes, say hello to every one of those slackers that aren't here.
Hi.
No, you have to speak the words, yeah. This is a microphone.
Oh.
This is the camera, but when I shined it on you yesterday, you guys just looked all dark in the shadow. Okay, so what we're going to be doing right now is the kinetic molecular theory. So, kinetic, this should be somewhat familiar to you. Kinetic molecular theory. Now, there are kind of two forms of this. So I'm going to call this the KMT, and we're going to focus on gases. Generally, in general, in the big picture, when we talk about the kinetic molecular theory, we usually say, oh, well, we have solids, which they vibrate against each other. We have liquids, which are flowing. They have a greater range of motion, so they slide all over each other. And then we have gases, where the molecules are just going every which way, right? That's the big picture kinetic molecular theory. What we're going to focus on here is the kinetic molecular theory as it pertains to gases. You have to know both. The big picture KMT is pretty simple, pretty easy. I think you guys have that down. The kinetic molecular theory as it pertains to gases is a lot more specific. Okay? So we have the big picture, or let's say the simple form of that. The simple form is the molecules are in constant motion. And you know they're vibrating in solid, they're sliding around on each other in a liquid, and they're all over the place on a gas. And the motion determines the phase. The type of motion, determines the phase. Remember, that's solid, liquid, gas. So this is the simple form of that kinetic molecular theory. Let me see if I can bump this up one more. If it'll let me.
Does that say phase at the end?
Phase.
Oh, phase.
And that's SLG, solid, liquid, gas. Now, what we're going to focus on here is the kinetic molecular theory, KMT, of gases. And in particular, we're going to talk about ideal gases. So an ideal gas means it basically follows all of the rules that we're about to go over. If it's an ideal gas, it follows the rules, and our calculations are much, much easier. If it's not an ideal gas, life is bad, and we don't want to talk about it. Okay? Some of these things are just pretty obvious, and you're thinking, okay, duh, why are they even saying that? So number one, gases are made of very small particles. Atoms or molecules, that's what they're talking about. That's the first thing. Got to be made of really small particles. The bigger the molecule, the more difficult usually it is. Not across the board, but usually it's more difficult to keep them in the gas form. Okay, so one, gases are made of small particles. Two, gas particles are so tiny in comparison to the distances between them that we can consider the volume of a gas particle to be negligible. Okay, let me say that again. Gas particles are so tiny compared to the spaces between them. Okay, that's the kicker. So what they're saying is there's this massive, huge gap between the gas particles. That's why they don't have a definite shape, right? Or a definite volume. We can squeeze them together and it's still a gas. We can spread them out, it's still a gas. If I open this pen right here, you guys ever, those Sharpies that stink? You know, when little kids are stupid, they open the Sharpies and they sniff the Sharpie. Yeah. Okay. So when you take the lid off the Sharpie, those gas, that ink is volatile. It changes to a gas pretty quickly. And those gas particles, they will spread throughout the entire space here. This whole area is open. Those gas particles spread throughout the whole thing. You could still find the pressure of the gas from that stuff. Because technically it's here, right? That's what they're saying. The spaces between the gas particles are massive compared to how tiny, tiny, tiny the particles are. Because the particles are so tiny, it's like we can ignore the volume of the individual particles. It's kind of like when we have the atom and we talk about the mass of the electron, don't we just ignore that? It's so incredibly tiny that's like, it's insignificant. Let's just ignore it and be done with things. So gas particles are so tiny compared to the spaces between them that we can consider the volume of a gas particle to be negligible. What that means is, for our calculations, the molecules have no volume. That's a big, big, big deal. That's what that means. When we're dealing with an ideal gas, we don't even have to take into account the volume of the particles. And it's not because they don't have volume, it's because compared to the gaps that are between the molecules, it's insignificant. It's kind of like saying, okay, so we have a 50-mile gap between Borger and Amarillo. But I'm going to step 1 foot away from Borger. Is that a significant amount? No, we can ignore that 1 foot, right? It's insignificant compared to the total distance. That's what they're telling you here. Yeah, there's a volume there, but it's insignificant compared to the overall space between them, because it's really the amount of space, the overall space that it takes up, that's going to be the volume, not the individual atoms or molecules that are in there. The third one, the gas particles are in constant motion, which you already know this. Moving in a straight line in random fashion. Okay, so the gas particles are in constant motion, moving in straight lines until they hit something, right? In a random fashion. There is no pattern, there's no set path. Colliding with each other and the container. Okay, so what's the container? Well, it depends on where you are. In most cases, our gases are not in little bitty containers, right? I mean, if you think about the vast majority of gases that we work with are right here, what we're breathing in it right now, right? So we could say the container right now is this, basically this whole open building, right? So the walls would be the container, the edge of the container. So gas particles are in constant motion. They're moving in a straight line, in a random pattern, and they hit each other. They hit the sides of the container. They collide with each other. And the collisions with the container are what cause pressure. You happen to be part of the container, right? Because you're not made of gas, you're made of a solid. And so when the gas molecules hit your skin, you're part of the container, and when they hit the container, that's what causes air pressure. So collisions with the container cause pressure. And pressure is basically force divided by area. So the amount of force per unit area is what it is. I don't know why it's beeping at me. I'm not going to stop. We're going to pretend that everything works beautifully. Okay? So right now, and it's not whether the container is the side, it's up, it's bottom, whatever, the atoms and molecules hitting you are causing pressure. As a matter of fact, right now, it's causing you about 7 pounds per square inch of pressure. Every square inch on your body is being hit with enough force to cause 14 pounds of pressure. 14 pounds. Think about a 10-pound bag of potatoes or something that weighs 10 pounds. And it's more than that. 14 pounds per square inch on your body. And that doesn't mean just on top. It's everywhere, because gases are moving every which way, right? They're not just moving down. So that pressure is caused by the gas molecules hitting the container. And it just so happens we're the solid in here, so we're part of the container. Okay? That's another part of the ideal gas law. I'm sorry, of the kinetic molecular theory. Okay, the next thing on here, number 4, gas particles neither attract nor repel each other. In an ideal gas, gas particles neither attract nor repel each other. What this means is there are no IMFs. Do you guys remember that word? Intermolecular forces. So there's no force. Here's one gas molecule. Here's another gas molecule. They don't attract each other. There's no force of attraction between them. So the gas molecules, they don't attract each other. They don't repel each other. There is no intermolecular force between them. So another way to say that is that, did we talk about IMFs? Have we used that? Have I used that term before? Yes? Some of you guys are saying, I don't know. Intermolecular force, IMF. What this means is there are no attractions between the molecules. This is a big key here. Now, what this means is when they hit each other, and this is going to be a physics thing here, when they hit each other, when they collide, they have perfectly elastic collisions. That's a physics term. Perfectly elastic collisions. Remember, this is an ideal gas, right? That means no kinetic energy is lost. So if they were not ideal gases, when they hit each other, they would slow down every time they hit something. And they would keep getting slower and slower and slower and slower until they came to a stop, right? That's a normal collision that you think of. In an ideal gas, that doesn't happen. Basically, when you've got gases right here, these are considered ideal gases, they don't stop. The molecules are constantly moving. So we have perfectly elastic collisions. All the kinetic energy is transferred from one to another. All that kinetic energy is transferred from one molecule to another. And remember, when we talk about kinetic energy, the equation is 1/2 times the mass times the velocity squared. So this kinetic energy, there's an average kinetic energy, and it's going to be transferred. There's no kinetic energy loss, which is weird. Doesn't happen on our big term because we deal with friction and stuff like this, but what they're saying is, hey, there's no friction, there's no attraction, there's no repelling, there's no nothing. That's how ideal gases work. And we can do all the calculations, and our calculations come out right following this kinetic molecular theory. Okay, I'm going to stop the video here so it doesn't get this huge, massively long video.